All right, let's get right into it. Today, we're going to break down the language of chemistry. We're going to go from the things you can actually see and touch all the way to the powerful equations that scientists use to describe it all.
So, let me start with a question for you. What does a rusty old nail have in common with a carton of milk that's been sitting out on a hot day? I know, it sounds like the beginning of a bad joke, but seriously, think about it. What's the hidden connection there?
And there it is. They are both chemical reactions. The very essence of the original substance changes into something brand new. That rusty nail isn't just iron anymore, and that sour milk is definitely not the same stuff you poured on your cereal. That complete transformation, that's the heart of a chemical reaction.
Okay, so how can you tell when one of these reactions is actually happening? Well, you don't need a fancy lab. You just need to know what to look for. Think of yourself as a detective, and these are your 4 telltale clues.
Here they are, the 4 big signs. First, you might see a change in state, like a liquid suddenly forming a solid, or maybe a change in color. Then there's the evolution of a gas, think fizzing or bubbling. And finally, a change in temperature. Does it get hotter or colder? If you spot any one of these, you're almost certainly watching chemistry happen right in front of you.
Let's look at a great example. If you burn a ribbon of magnesium, you're starting with this solid, shiny metal. But afterwards, you're left with a totally different white powder. That's a change in state and a change in color, all in one go. Not to mention that dazzling light it gives off.
Now for the other 2 clues, check this out. When you drop zinc into acid, you see all those bubbles forming? That's our 3rd clue, the evolution of a gas. And if you could reach out and touch that test tube, it would feel warm. And there's our 4th clue, a change in temperature. See? Simple examples, but they show all 4 signs perfectly.
Describing these things with full sentences works, but it's a bit long-winded. Scientists needed a much better, way more efficient language to tell these chemical stories. So let's see how that language developed.
Just look at the difference here. On the left, we've got the long description. It's clear, but it's a mouthful. Now look to the right. The word equation. Magnesium plus oxygen, that arrow means yields or becomes. Magnesium oxide. It's so much cleaner, right? It tells you what you start with and what you end with. Simple.
And this introduces some really important vocabulary. The things on the left side of the arrow, our starting ingredients, are called the reactants. And the new stuff on the right side, what you end up with, is the product. It's easy to remember. Reactants react to produce products.
But why stop there? We can get even more concise. Instead of writing out the words, we can just use the chemical symbols for everything. Mg for magnesium, O2 for oxygen, and they come together to make MgO. This is a real chemical equation. It's like the universal shorthand for chemistry.
But wait, hold on a second. There's a little problem here. This is what we call a skeletal equation. It tells us what ingredients are in the recipe, but it doesn't tell us the right amounts. And in chemistry, that's a huge deal. The story isn't quite right just yet.
And that brings us to a really critical step, the balancing act. Because to tell the chemical story correctly, we absolutely have to follow a fundamental law of the universe.
And here is that law, the law of conservation of mass. This is a cornerstone of all science. Put simply, it just means you can't create atoms out of thin air, and you can't make them vanish into nothing. Whatever you start with, you have to end with. It's just rearranged.
So, if that law is true, then we've got a problem. How do we explain an equation like this one, showing iron reacting with steam? Because when you look at the number of atoms, it seems like we're breaking the law left and right.
Just look at this table for a second. On the left side, the reactants, we start with 1 single iron atom. But on the right side, the products, we magically end up with 3. And look at oxygen. We start with 1 and somehow end up with 4. This equation, as it is unbalanced. It's telling an impossible story.
So how do we fix it? We balance it. We can't change the formulas themselves, but we can change the number of molecules. So first, let's put a 4 in front of H2O to get our oxygens to match. But that gives us 8 hydrogens, so we need to put a 4 in front of the H2 on the other side. And finally, we need 3 iron, so we just put a 3 in front of the Fe.
And now, let's look at the result. 3 iron on the left, 3 on the right. 4 oxygen on the left, 4 on the right. 8 hydrogen on the left and 8 on the right. Perfect. Every single atom is accounted for. The law is upheld. The equation is now balanced.
We can even add more detail by showing the physical state of everything, like S for solid and G for gas. This equation is now totally complete. It tells us what reacts,
what's produced, in what amounts, and in what state. This is an accurate chemical story.
Okay, so now that we've got this powerful and accurate language, we can start using it to classify and understand the incredible variety of chemical reactions that are happening all around us, all the time.
Let's start with a really simple one, a combination reaction. And honestly, the name gives it away. You take two or more separate things, your reactants, and they combine to form one single, more complex product.
A great real-world example of this is mixing quicklime with water. These are two totally different reactants, but when you mix them, they combine to form just one product, something called slaked lime. It's a key ingredient in things like cement and plaster.
And what's really fascinating is that many of these combination reactions are also exothermic, which is just a fancy word that means they release heat. But here's the truly amazing part. The reaction happening inside your own body right now to give you energy, respiration, is also an exothermic process. You are literally powered by a slow, controlled chemical fire.
So, think about it. We've gone from a simple rusty nail all the way to understanding the very reactions that keep you alive. You now have the key to deciphering this hidden world. So, the question I'll leave you with is this. As you go about your day, what chemical stories will you start to notice unfolding all around you?